Okay, here we go. This is the final exam review, part 2, walkthrough. All right, here we go. Number 1. The category of elements we're looking for here is the metals. Okay, malleable, ductile, conduct electricity, relatively high melting and boiling points. Those are the metals. Nonmetals tend to be gases, not good conductors. Metalloids have properties of both. Okay, you need to know your groups of the periodic table. There are names for groups 1, 2, 17, and 18. Okay, group 1 is the alkali metals. So that's what we're looking for here. Group 2 is the alkaline earth metals. Group 17 is the halogens. Group 18 is the noble gases. And then the groups in the middle, groups 3 to 12, and the F block down at the bottom, those are called the transition metals. So you need to know those groups. Okay, the valence electrons. If the valence electrons are the same, those elements will be in the same group or column. That's going up and down. Okay, that's how they're grouped. They're grouped in columns by the number of valence electrons. So the number of valence electrons is based on the column or group. The energy level that those electrons are in is based on the row going across. Okay, number 92, uranium. Heaviest naturally occurring element. A and B are both man-made, and D is not a real element. So there were several people who tried to develop periodic tables that were similar all around the same time. The reason Mendeleev's was finally accepted is that he understood the pattern well enough to realize that there were certain elements hadn't been discovered yet. He was so convinced that the pattern worked that he left blanks in his periodic table where there was no element that fit, because he believed that they would fit. They would be discovered later, and then they would fit into that place, that were later discovered and that fit exactly where he said they would. So that is why he's given credit for creating the modern periodic table. However, he was not the first to put them into a table. That credit goes to Lavoisier. Lavoisier was the first attempt to categorize elements based on similar properties. Okay, so we have a duplicate question here. Okay, a gas at room temperature and non-reactive. The unreactive classification is important. Halogens are highly reactive, and noble gases are called noble because they don't interact with others. They don't mix. Metalloids. Okay, there are only a few of these. Magnesium and copper are both metals. Neon is a noble gas. Silicon is a metalloid, and if you look on your periodic table, there's a zigzag line that goes down the side of the periodic table. All of the elements that touch that line except aluminum are called the metalloids. So you might want to mark that down on your periodic table. The octet rule says that all elements want 8 valence electrons in their outermost shell because that is the most stable arrangement. Okay, and the way you get 8 valence electrons is by filling up the s and the p orbitals, because the s can hold 2, the p can hold 6. That gives you 8 in the highest energy level, so that's going to be A. The key here is, do you know the 4 blocks of the periodic table? So I'm just going to label them. The 2 on the left are the S block. The big chunk in the middle is the D block. This square section over here is the P block, and then down below is the F block. The F block, again going back, this section that's always or usually down here by itself with 2 long rows, 14 columns across, that is the F block. The atomic numbers of the elements go from top left to bottom right, increasing as you go across from left to right. If they're right next to each other, that means that they're each one proton different from the one on either side. All right, fluorine and iodine are both halogens. If you find elements in the same group or column, that means that they're going to have the same number of valence electrons. Okay, a cation is an ion with a positive charge. The term for a negatively charged ion is anion. Iron 3 oxide. Okay, which is the metallic ion? First of all, iron is the metal, and then the question is it -2 or +3? Well, the Roman numeral in the middle tells us that it's a charge of 3, so that rules out choice B. But also remember that the first name in the first element named is always the positive and then the second part of the name is always the negative half. Okay, this correct formula for sodium phosphate, which is PO4 with a charge of -3. There are several others that you need to know, like ammonium, that's the only positive one, hydroxide. If you don't have the notes on that, just check in with me in class and I will let you know which ones you have to know. PO4, which is a -3. Sodium is in group 1, which means it has 1 valence electron, so it's going to lose that valence electron and form a +1 ion. Again, there are ways to figure this out using the periodic table. I'm not going to go through the whole thing here. If you don't have the notes or need a reminder, check in with me. Another good thing to label on your periodic table is what are the charges of the representative elements. Okay, so I've got sodium, which is a +1. I've got phosphate, which is a -3. I can't make the -3 charge any smaller because one phosphate has a charge of -3. But if I add 2 more sodiums, that gives me a total charge of +3, which would be the same over here as the -3. So it takes 3 sodiums for every phosphate. So the formula is Na3PO4. The key here is oppositely charged particles. Okay, covalent is formed by sharing electrons between 2 neutral atoms. So when you have oppositely charged particles called ions, the attraction between them is an ionic bond. We've got boron, which has 3 valence electrons, and chlorine, which has 7 valence electrons. How are they going to combine? What ratio? Well, boron is going to form a +3 ion. Chlorine is going to gain 1 electron. Right? If it's anything less than 4, it's going to end up being a positive charge. If it's more than 4, it's going to be a negative charge. Chlorine is -1 because it needs to add 1 more electron to get to 8. Boron is a +3 because it's going to get rid of all 3 of those electrons. Can't make the 3 any smaller, but if I had 3 chlorines, each one with a -1 charge, that's a total of -3. So I need a boron, and then I need 3 chlorines to cancel it out, which is choice D up here. So we've got a formula. These numbers, these subscripts, tell you how many of each element or polyatomic ion there are in this compound. So in 1 mole of this compound. So this little 3 tells me that there are 3 moles of magnesium per 1 mole of compound. If I've got 3 moles of compound, I have to multiply that by 3. Which gives me 9 moles of magnesium. How do atoms become more stable? Well, they become more stable by forming bonds with other atoms and either sharing electrons or by transferring electrons to get to a full outer shell. Metallic bonding, malleable and ductile, you need to know what those words mean. They do have that. Metals are typically good conductors of electricity. Most metals are solid at room temperature. But if you think about a metal, they don't boil at low temperatures. Okay, this is what is not a property of metallic bonding. Bond energy is the term we give to the energy it takes to break a bond. And when the atoms bond, they hold on to each other, and it takes a certain amount of energy to pull them apart. It's a measure of how strong the bond is between 2 atoms. Covalent bonding is the sharing of valence electrons. Ionic is complete transfer. Covalent is shared valence electrons. What type of bond do you get when you have carbon and oxygen bonded together? When we're looking at the electronegativity, and the reason this is on here, is that you want to look at 2 atoms that are bonded together and then compare their electronegativities. Right? The difference between these 2 electronegativities is 1.04. So what does that mean? Well, if the difference is less than 0.4, then we call that covalent. Okay, it's basically even sharing of the electrons. If it's between 0.4 and 1.7, then that's called polar, because what it means is there's a significant difference between the attraction that each atom has for the electrons. If the difference is between 0.4 and 1.7. We call that a polar bond, a polar covalent bond, because the attraction on one side is going to be stronger than the attraction on the other side, so that one atom is going to attract the electrons toward it most of the time, but not strong enough where it's greater than a 1.7 difference, because that makes an ionic bond where the difference is big enough that one atom can completely take the electron for itself. In this case, we have 1.04, which falls into this middle range, which makes it a polar covalent bond. Okay, this time we've got 3.16 versus 1.00. The difference 2.16. So that's above, okay, greater than 1.7. So this means that the chlorine has such a strong pull on the electrons, it's going to completely remove one of the electrons from calcium. So that makes it an ionic bond. Once the electrons are transferred, it's called ionic. The strength of covalent bonds is determined by the length. Longer equals weaker bond, and shorter bonds are stronger because the atoms are getting closer together, so the attraction between them gets closer and gets stronger. And when you have multiple bonds, each bond gets shorter and therefore stronger. Shorter is stronger. Electronegativity, you've got to remember that as you go to the right and as you go up, it gets stronger. Electronegativity gets stronger, and the group, the noble gases over here, does not count. So the strongest electronegativity is fluorine, and the closer you get to fluorine, the stronger the electronegativity. The farther away you get from fluorine, the weaker the electronegativity. So the one of these elements that's the farthest away from fluorine is boron. Name the compound NBr3. We have two nonmetals here, nitrogen and bromine, which tells you that this is a covalent compound. The electrons are going to be shared. And the way we name covalent compounds is you name the element, the first element, and since there's only one nitrogen, because it has no subscript, we don't put a prefix on the first element if there's only one. The second element, first of all, we put the root of the element name, and we change the ending from bromine to bromide. And then to indicate how many bromines there are 3. We have to put a prefix on here. The prefix for 3 is tri. So you need to know the prefixes, and I'm not going to put them all down here, but mono, di, tri, tetra, penta are the most common ones, but you really should probably know all of them from 1 to 10. If you don't have that written down, come see me and we'll get the rest of them for you. A triple covalent bond, okay, so between two atoms, how many sigma and how many pi bonds are in here? Well, there's always one sigma bond in any bond, whether it's a single, double, or triple. There's always one sigma bond. If there are double or triple bonds, then the other bonds are called pi bonds. So a triple bond is 1 sigma and 2 pi bonds. If it was a double bond, it would be 1 sigma and 1 pi bond. A single bond is just 1 sigma bond. Okay, hydrogen bonding. The name is a little misleading because it's technically not a chemical bond. It's what's called an intermolecular force. Okay, London forces, dipole interaction, and hydrogen bonding are the major types of intermolecular forces. And this is also called dispersion, the London forces. So just know what those are. And if you saw, for example, hydrogen bonding in a diagram, you need to know that it's an intermolecular force. And also remember that intermolecular forces, any of them, even though hydrogen bond is a really strong intermolecular force, it is still weaker than a chemical bond. So if you're given a choice between hydrogen bonding and ionic bond or covalent bond or even polar covalent bond, okay, all of those are stronger than hydrogen bonding. We're going to do formulas for these compounds. So these are ionic compounds, which means we have to use the charges to figure out the ratio. So for the first one, you've got calcium, which is a +2. Again, if you don't know how to figure that out using the periodic table, you need to come talk to me and we'll go over that. Bromine is a -1. So it would take 2 bromines to add up to the charge of 1 calcium, +2, and now I've got -2 if I put 2 bromines together. So the formula is CaBr2. Iron 2 oxide, the 2 in the name tells me that this particular iron atom has a charge of +2. Iron and most of the metals in the middle, the D block of the periodic table, can have more than one charge. So we use the Roman numerals to indicate what charge are we talking about in this case. So iron in this case is a +2 because that's what the Roman numeral tells me. Oxygen is a -2 because it always is. And then if you just look at it, if I took 1 oxygen and 1 iron, that would be +2, -2. They cancel each other out just like that. So FeO is all you need there. Sodium sulfate. A sodium is a +1 sulfate. Don't look for it on the periodic table. It is a polyatomic ion with a charge of -2. So that means I need 2 sodiums to get my charge to plus 2, and that will cancel out the minus 2, so it gives me Na2SO4. And then the last one, ammonium phosphate. Neither one of those things is on the periodic table. Ammonium is a +1. Phosphate, we've seen once before, is a -3. Can't change the -3, but I can pile up extra ammoniums, come up with that +3 charge. 3 ammoniums together gives me a +3. 1 phosphate gives me a -3. When you put a polyatomic ion like ammonium into a formula and you need more than one, put it in parentheses, put the number of them outside the parentheses, and I don't need parentheses around the phosphate because there's only one of them. Okay, name the compounds. Well, naming ionic compounds, for the most part, you take just the name of the first element and then take the name of the second element and change the ending to IDE. Okay, we don't need to put prefixes like mono, di, tri on this because there's only one way for these two elements to combine where the charges would cancel each other out. So we can figure that out without getting into monosodium monochloride. Copper is a transition metal. It's from the middle of the periodic table, so I need to figure out what charge does it have. Well, there's 1 copper and there's 1 oxygen. I know that oxygen has a charge of -2 because it always does, which means if there's one of those, the total negative charge is -2. And there's 1 copper to cancel it out. So it must have a charge of +2. Otherwise, they wouldn't cancel each other out and they wouldn't be a valid compound. So that means that the copper has a charge of +2, which I need to indicate with a Roman numeral. And then oxygen becomes oxide. Magnesium, and then OH is hydroxide. Whenever you've got a polyatomic ion, you don't change the name. You just use the name of the polyatomic ion, whether it's phosphate or hydroxide or carbonate. Okay, so magnesium hydroxide, again, no prefixes in ionic compounds. And then this one we actually had in the last problem was ammonium. That's what NH4 is. It's not on the periodic table. And phosphate. Again, those are both polyatomic ions. So we have a combination. Ammonium is the only positively charged polyatomic ion that we work with. So just keep that in mind. All the other ones are negative. Now we're doing covalent compounds. Okay, here's where you need to know your prefixes. Dinitrogen, di means 2. Trioxide means 3. You use those numbers in the formula. N with a 2, O with a 3. Dinitrogen trioxide. Phosphorus with no prefix means 1, P. Penta is for 5, so phosphorus pentabromide, PBr5. Carbon, no prefix means 1. Tetra means 4. Fluoride means fluorine, CF4. Okay, name the compounds. This is the same one as was on the last slide. We need a di prefix in front of nitrogen because there are 2 of them. Dinitrogen, and then there are 3 oxygens, which means trioxide. So change the ending of the second element, put the prefixes on it as needed. The second element always needs a prefix, so even if there's only one, you put the prefix mono on it. But you don't put a mono in front of the first element if there's only one. So carbon, only one of them, so we just call it carbon. There are 2 oxygens, so dioxide, carbon dioxide, CO2. And PCl5, okay, P is phosphorus. There's only one of them, so it doesn't need a prefix. And then 5 chlorines, 5 is pentachloride. And then the last one is similar to part B, but there's only 1 oxygen this time. So the first part is the same, carbon, just 1, no prefix. But the second element always needs a prefix. There's only 1 oxygen, so we call it monoxide. You don't have to say monooxide. Lewis dot structure. So this is NaSl. All right, N stands for need, which is how many electrons would you need if you could give each atom all of the electrons it wanted. Not how many does it need to fill up its shell, but totally how many does it need. So anything that's not a hydrogen needs 8, and hydrogens always need 2. In this case, there are 3 oxygens, so they would need 6. So altogether, you need 14 electrons. How many electrons do you have available? That's what the A stands for. Well, nitrogen has 5 valence electrons. Hydrogens have 1 each, and there are 3 of them, so a total of 3 valence electrons can be contributed by the hydrogens. So that number is 8. Again, if you need help figuring out the number of valence electrons, that's a great thing to put on your folder with the periodic table, and I can help you with that. So I need 14, but I only have 8. S is the number of shared electrons. So I'm going to share 6 electrons. Remember that it takes 2 electrons to make 1 bond. Okay, so 6 electrons means I'm going to make 3 bonds. And then L is for lone pairs or leftovers. I had 8 electrons available. I shared 6, which means there's 2 left. Those are going to be dots that we put around at least one of the atoms. So if I lay this out, nitrogen, it's usually the first element in the name that goes in the middle. And then there are 3 hydrogens. You put 1 on each of the 3 sides. There's nothing on the 4th side. I said I was going to share 6 electrons, which makes 3 bonds. 1, 2, 3. That's it. I used up my shared electrons. And I've got 2 left over. Dots are the L. Never ever put dots on a hydrogen. Can't do it. Can't work that way. So that leaves the only place left as this empty side for nitrogen over here to put those 2 dots. And that makes sense or works out because now if you look, this hydrogen has 2 electrons connected to it, 1 on either end of the bond. This hydrogen has 2. This hydrogen has 2, which is what they all want. And then this nitrogen now has 8 connected to it. So they all have as many electrons as they want. Going down to B, NaSl again. How many do I need? Well, there are 3 atoms here. There's no hydrogen, so I do 8 times 3. So I need 24 electrons. How many do I have? Carbon has 4, oxygen has 6, and there are 2 oxygens, so that gives me 12. So I've got a total of 16. 24 minus 16 is 8. That's how many I'm going to have to share. And then the leftovers are going to be 16 minus 8, which is 8. So you just subtract as you go down. Carbon has to be in the middle. It's pretty much always in the middle. And since there are 2 oxygens, it has to be in the middle. I'm going to share 8, which means 4 bonds. 4 bonds, but I only have 2 places to put bonds. I can put 1 here and 1 here. And then I need 2 more bonds. So the only thing to do is to double up. If I needed another one, I would have to triple up. And always put the bonds as evenly as you can. Don't put 3 on one side and 1 on the other. That wouldn't be right. And then the dots. You always want to put dots on the outside atoms first, unless they're hydrogen. Never ever put dots on a hydrogen. So I've got 8 leftover electrons. If I put 4 on each side, I always want to try to split them as evenly as you can. Now look at your distribution here. Okay, if you look at the carbon, it's got 4 bonds. Remember, those 4 bonds equal 8 electrons. So carbon has 8 connected to it. Oxygen has 2 here, 4. The 2 bonds make up 4 electrons, and then it's got the 4 dots on each end. That makes 8 for oxygen, 8 for carbon, and 8 for the other oxygen. So that is everybody satisfied with the octet rule. Based on the shapes above, what are the shapes, based on the molecules above, what are the shapes of the molecules and whether or not they are polar? Well, you have to remember there's a little chart, and again, I'll give it to you. If you don't have it in your notes, I can help you with it. That tells you, you look at the central atom, which is the one in the middle, so the nitrogen here and the carbon here, and you see how many bond areas there are. This one has 3. This one only has 2 bond areas, even though there are 4 bonds. The double bonds equal 1 area where there are bonds. Or the other way to look at it is how many atoms is the central atom connected to? The central atom for carbon is connected to 2, 1 on either side. So it has 2 bond areas. And then look at any lone pairs. So this has, the nitrogen has 3 bond pairs, or 3 bond areas, regions we'll call them, and it has 1 lone pair. The carbon has 2 bond areas, bond regions, and 0 lone pairs. Okay, then there's a little diagram that you have to look up, and you find, well, what is the shape called when you have 3 bond regions and 1 lone pair? What is the shape called with 2 bond regions and no lone pairs? You'll find that this is called trigonal, pyramidal, and that the other shape is called linear. straight line. And then the question is, are they polar or not? Well, the easiest thing to look at is if you look at the CO2, we'll do that one first. The CO2 is the exact same thing on both ends. So even though the bonds in here may be polar, the oxygens may be hogging most of the electron, which makes each end of this molecule a little bit negative, it's negative on both ends. In order to be polar, it has to have a negative side and a positive side. So a straight line, what's the same on both ends, is always going to be non-polar. And then if you go back and look at the NH3, the ammonia, this has three sides that are the same, which are hydrogen. The hydrogen parts of these molecules are usually going to be at least a little bit positive. And then it's got this area up here, which is negative because it's got lone pair electrons, which are negatively charged. So it's got positive charge spread around the bottom, it's got negative at the top, and that makes it a polar molecule. And I can help you with that if you're having trouble. And that's it for part 2. Moving on to part 3, and the video for that will be up tomorrow morning.